I'm Ron Knapp. I'll be talking on convex optimization, which is optimization for convex functions on convex sets.
So Roger worked with Boyd, and he's been talking about it for years and years. And I always thought, when Roger was talking about convex optimization, I sort of get this picture of a balloon in my head and sort of imagine, optimizing over blobby objects and stuff, which in a sense is what it is. But it's actually a lot more than that. There's a whole set of things that are available. And the big thing about it, before I even get started, is that when they figured out the simplex algorithm, and so linear programming then became a solved problem, in essence. And so a whole wide array of applications opened up for that. And basically the same thing is true for some of these fields of convex optimization, like semi-definite optimization and some other things. So now we have a much broader thing, which is sort of an essentially solved problem. And so we can access libraries that will solve problems as long as we can map into these various forms. So I'm going to sort of talk today about some of those mappings and what we're trying to do within the Wolfram language to be able to make that accessible. So first, let's define. I'm going to get a little mathy for a while, so bear with me. Okay, so I'm going to make some definitions, and I'll talk about what convex optimization is. So here are a few basic definitions. So a set is affine if you can add any two elements in a combination, theta plus 1 minus theta of x. And that combination is also in the set. So a set is convex if it's affine with the theta being greater than 0, actually between 0 and 1. Okay, and a function is convex if f of theta x plus 1 minus theta y is less than or equal to theta f of x plus 1 minus theta f of y. Okay, and another important definition that I'm going to use a lot, take advantage, is this thing called the epigraph. The epigraph of a function is a set xt, so that x is in the domain and f is less than or equal to t. And the epigraph of a convex function is a convex set. And that's sort of how a lot of this convex optimization stuff works. So let me, oh, you know what? I can't see. Huh. Let me check. Okay. Well, I had this very nice manipulate cell for you to show you what all those things were, but it seems to have disappeared, so I don't know where that's gone. But okay, so here's a big thing about convex optimization. So we'll call the optimization problem to minimize some function of x. Okay, and this is just the classic optimization problem with f, so a bunch of constraints with functions and some equality constraints. Okay, and it's going to be called a convex optimization problem if all the fi's are convex functions and the hij's are affine functions, or mainly they're linear functions. And then we have what's called a convex optimization problem. And the big thing, or actually the really smallest thing, is that this. So for a convex optimization problem, a local min is also a global minimum. So that's one of the huge things. So you don't have to search around. There are no extra bumps. It's got to be a global minimum. So any convex minimization method is actually a global minimization method. And that's one of the reasons these problems can sort of be considered as solved in some sense. And that's really important. Now, another thing is using this epigraph idea. I can always write a convex optimization problem in this form. So minimize t so that f of 0 minus f of t, and this is sort of called the epigraph transformation. So if you have a convex function, this is basically the epigraph. The f of x is less than or equal to t, and I'm going to use that in transformations we do with these problems. That gets used all the time. So then I have these. So basically, a linear objective function and linear equality constraints are ubiquitous. So I'll be mostly talking about things with linear objective functions, or I'll translate to something with a linear objective function. Okay, so basically it's all about cones. Okay, now I would have preferred to use Dan Aykroyd and Gilder Adner than myself, but I wasn't sure about the copyright for that, so I did this. And also people have said my appearance has been changing slightly since I started working on this project, so thought I might as well show you. Okay, so the particular cones we're going to be talking about are what we'll call convex proper cones. So a cone is a set if you have, for any theta positive, if x is in the set, theta x is also in the set. So it's basically kind of what you think of as a, the classic cone shape. Now a convex cone is a cone that also satisfies convexity. Now this is written in a slightly different form because I'm taking advantage of the theta x term, but basically any combination for two thetas greater than 0 has to also be in the cone. Now a proper cone has a non-empty interior, so basically it has to be full dimensional in a set, and it also has to be pointed. Namely that if you have a set that's both in the cone and x minus x is also in the cone, then that element has to be 0, and that's the point. The point of the. So let me show you a couple of pictures. This is our classic cone, the one we probably all think about. Okay, so that's a cone. You can see I start here. I multiply by any multiple, positive multiple. It's always going to be in the cone, and any two combinations will also be in the cone. And this is actually one of the cones we'll be using to map to the convex optimization for. Here's something that is a cone, but it's not a proper cone, okay? Because it is full dimensional, but it has this thing here. So there's no there. So I can have this value, I can have this value and minus value. They're both in the set, but they're not the same thing. So it's not pointed. It has to be pointed in all the dimensions. Okay, so here are some common cones that we're going to be dealing with. So the first one is often called the positive orthant cone as well. The norm cone is often called the second order cone, and the semi-definite cone, and then these are a little bit, and a huge number of problems. I mean, there's a huge number of papers that show how you can map different problems into those first three cones. There are some more papers that show you how to do these other cones, but the first three are very common and cover a huge wide set of application classes. Okay, so now let's talk about something we can do with cones. So suppose we have a proper cone. Then you can define a partial order based on membership in that cone. And this is as follows. And it's a little hard to see in these fonts that we have now. We'll eventually have a good character for that. But we have x is less than or equal to, by the cone order, y, if and only if y minus x is in the cone. And the greater than equal is basically the same thing with the sign reversed. So that sort of sets up a partial order. So, and we've actually set this. These are going to be important to our. Don't worry about the messages; those ideally shouldn't be there. But we have commands called cone less equal and cone greater equal that allow you to specify these things. And you can ultimately, once this development version comes out, you'll be able to use that curvy equal to indicate that as well, which will be tidier and neater. So the two really frequent cases are the non-negative cone and the semi-definite cone, and they're quite distinguishable because this is for vectors, this is for matrices, so you can specify those without the actual cone given, and we'll figure out which one you actually mean. So these actually evaluate if we have things numerical. So suppose I set up a set of random real, and I check to see if it's cone greater than equal. That means all elements are positive. Okay, now 0 is a special case. So this doesn't fit into the definition because this is a scalar, not a vector. However, if I add, plus 0 dot. So when I make that right-hand side a vector, then it evaluates, and that's now false because not all elements are greater than 0.1. So that's element-wise comparison. This is actually a really fast way to evaluate that if you need to do that for other reasons than optimization. So we can set up a matrix. I'm to set up a Kronecker product of the vectors. Okay, that is true. That evaluates to true. So that means that MX should be a positive semi-definite matrix, because without the cone, if it's a matrix, it's interpreted as a semi-definite cone. So we can check. Well, not quite. Okay, I mean, actually, theoretically, if I take a product, two matrices, it should be positive, but because of numerical error, the eigenvalues come out a little bit negative. And so when we actually do this, there's some tolerance included. And it's sort of the same tolerance as included in this command. It actually works by using this command, positive semi-definite matrix. So there's always, remember when we're talking about these things, there's always a little bit of tolerance involved. Okay, so now let's talk about another class of optimization, which I'm going to call conic optimization. Okay, and this is a subclass of convex optimization, but it's one that's particularly useful because we can map problems into this and use features of these cones to actually put together solvers and solve the problem. So this is kind of the set that's actually a solved problem. So we're going to have a linear function. Again, that represents any convex problem. Okay, but we're going to have affine mappings. Okay, so a1x dot b has to be in some cone, which I'll call k1, and so on and so forth. So I have n cones, and then I have the linear equality constraints, which goes with the convex part. So I have n cones, okay, and these are proper cones, x's vectors, and so on and so forth. And basically, so the whole set that I'm thinking, you can combine cones. So this could actually be written as a single inequality over the tensor product of all those cones. So it's a cone. So it turns out that linear optimization or linear programming is just a special case of this. Okay, so it's a1x.b1 is, and I'm using a cone greater than or equal, and the cone here is the non-negative cone of size n, where n is the number of inequality constraints. I have the equality constraints, and so that's, now there's other standard, this is the way that Boyd and a few authors write the conic problem. There's another standard way of writing it that involves the x being in the cone. It's always, just as it's possible to write to linear programming, you've probably gone through this exercise at some point where you'll write so all the variables have positivity constraints and stuff like that, and it's a bit of a pain in the rear to do that, but it is possible, and it's possible for these as well. There's also a dual form. I just don't have time to talk about the dual forms, but those are actually very important in solving and getting sensitivity and various things like that. So in another way yet, I'll just mention to express the conic problem, is this. So instead of writing as inequalities, the equivalent expressions are that this set, so this affine mapping of x has to be in cone 1, and so on and so forth. So it's element-wise. And that's going to be important in what I'm going to set up as the canonicalizations, which I'm going to call, Jose helped me find this name. We call it cone transformation now. It's probably not the right name, so if you can think of a better name, you'll let me know. But basically, the idea is we want to say, so that's the set of x such that ax plus b is in some cone. Okay, so let's set up, I'll show you an example. So I have this set, and this is actually, this is a set, okay, so I can actually plot it. So this one, it's the non-negative cone. And if you think about it, I've actually got three inequality constraints. So I have x is greater than or equal to 0, y is greater than or equal to 0, and minus x minus y is greater than or equal to 2. Okay, and it turns out to be this polyhedron. And in fact, the set of affine constraints of the non-negative cones are the polyhedra. It's the polyhedral cone. So that's a common thing. Okay, another way to look at this is equivalent to a dot x plus b is greater than 0. So these are the things that have to be greater than 0. And of course, again, maps to this triangle. I could plot that, and I get exactly the same plot. Okay, so let's look at, so now what I've done this is not an 11.2 yet, or even 11, but it's a prototype command, which I've called conic optimization. So I can set the vector for the linear function. So this basically means minus x minus y if I'm thinking of two variables, so it was before, and I can just call x min as conic optimization. So what it does is it does the optimization over that set, which is defined by those cone transformations, and I get a result. So let's look at the result and see if it makes sense. And sure enough, because minus x minus y, basically I'm maximizing the linear function going in this direction. If you think of minimizing going this direction, and that's going to have the biggest sum of x and y. So that's a simple linear programming problem. So now let's make another example with a different cone that's a little bit more interesting potentially. Okay, so I'm going to set up a disk. Okay, this is actually another representation of a disk. Okay, let's plot it and see. Okay, and I don't have time to go in and explain exactly how that actually looks is a disk, but if you do the mapping, you'll see that it is. And now I can do something like this, conic optimization of C, the same C in the disk, and sure enough, it comes up with square root of 2 is square root of 2, because if the linear function is decreasing this way, the minimum value is going to be there. So now let's do and again, this norm cone, for example, can represent a huge number of sets. I'm just going to show you, so this is the same, I've just put in a random matrix instead of the one I chose to represent the disk, and I've got all these sets represented, and I get something different every time. So you've got things like tubes and weird parabolas and so on and so forth. So there's a lot that can be represented just by the norm cone sets. Okay, so now let's look at the more interesting problem, which is so let's take that first set, which is the triangle in the disk, and do conic optimization over that. And now I get a result. So what does that actually look like? It's this. Okay, but notice I did a manipulate. So as I change the direction, this is changing the direction of the linear function by the locator. It goes on different parts of the disk. And here, notice it jumps, because along the line, it's completely indifferent. I mean, these are all going to have the same minimum values. These are outside the set, but along here, it makes a difference where you chose. So that's why it jumps in that weird way. Okay, so let's look at the idea of a convex modeling. So I've set up, this is sort of a very prototype command, which is actually for my debugging. I can write out, so I don't think you're going to want to construct these cone transformations on your own. I've sort of figured out how to do it because I've been working with this stuff for a few months, but it's hard going. Probably what you'll want to do is solve the equivalent problems, which might look like this. So you want to might minimize this, and so what the other part of what we're working on, so we're working on this canonicalization that gets us to the solvers. We're also working on something that works from problems like this, okay, to get to conic optimization problems that we're going to be able to solve. So this has an input form, okay, and I can write this, and sort of the command that I put together is a prototype, and eventually what this will be is this will just be in find minimum and end minimize, and you'll just be able to use those and take advantage of all this stuff. But for now, we've got this development version, so this is this command which I call convex minimize, okay, and it solves that problem, and that gives me essentially the same answer, but actually, interestingly enough, it's a slightly different answer. Okay, so and the only difference between those two inputs is I have the inactive norm and the norm. And I'm going to use that example to kind of go through the process we're going from a problem in terms of inequalities to get to the conic optimization problem. So I'll use that sort of as a platform to explain. So I've set up this thing I've called minimization problem, which allows you to input a problem. The idea of that is to have a structure. It's sort of like an ND-solve state data thing where we can do changes and transformations and eventually get the problem into the form where we want to solve it. Okay, so this is what the one with the evaluated norm. So norm evaluates symbolically, which is the reason for the difference. So what I'm going to do, I've got a function I also call transform problem. What it does is it transforms that into a form that can be recognizable, okay, to the things that actually make the conic mappings. So it takes away, it does this square root by something called a monotone transformation, because square root is a monotone function. Since the other side is just a constant, I can get rid of the square root. Abs of x squared is just x, or just x squared, so I can get rid of that. And so now I get with a quadratic function. So now I have a mapping from a quadratic function that works like this. So I have to map a quadratic function. A quadratic function can always be represented by a second order constraint. And a general rule works like this. So if I take a function x, y, s minus t over 2, dotted with itself, and then I take s plus t over 2, that comes out to x squared plus y squared minus st. That's a so-called rotated second order cone. So I can create, basically, if I have something like this, I can create a one longer second order cone that's going to do that. So I end up with, again, not time to do this, with this representation of the disk. And just to convince you that this is the same thing, I'll plot it. Sure enough, it's just the disk. So it's the same thing, but it's a different representation. And when the numerical methods actually work with that different representation, they get slightly different results. And that explains the difference of results. So the transformations in mapping can make a, but that I think gives you an idea of what's going on with the mapping. Okay, so we're getting short on time. I have a couple more examples to show you. So this is a semi-definite example, some using the modeling thing. So this is the idea. You've got a bunch of matrices, and you take A0 plus A1x plus A2x. You want to find values of the vector x to do various things. So what I'm going to do is I'm going to try and choose a combination of matrices at x's so that I can combine this A0 and A1 to minimize the spectral norm, or the 2 norm of that. Okay, so I'm using a technique which is very common with a semi-definite programming, is using the Schur complements. And so one thing I want you to notice is that I've entered this is a matrix, and I've entered this as a block matrix, and the processing automatically recognizes that. Another thing the processing is doing, and I can say I want this x to be a vector of length k, which in this case is 2. So I can just enter that and solve it, and it finds a solution. And now let's look at the plot of that. And what's interesting about this plot is, yes, it is actually the minimum, but notice this has a crease and dimples, so it's not actually smooth or continuous. So let's, I can do a bigger problem that generalizes. Let me do one more example to show you sort of the extent of the transformation stuff. Okay, so this is a geometric programming problem. Basically, I'm trying to maximize the volume of a box that satisfies the thing. So the volume of a box, I've taken 1 over to make it a minimization problem. Everything is positive. I can call this transform problem. And here it's transformed everything to exponentials. So this problem, actually as posed, is not convex. But under a transformation, d equals log of d. I've kept the variables the same. It does become convex with the exponential function because it's convexed. And then I can actually solve this problem by that, and I get the minimum of my box.
Are you just taking the negative instead of the reciprocal?
Well, the problem is to do that convex transformation to x, everything has to be positive. So that's a trick for this particular sort of problem, but that's a good question. Okay, so that's that. I'm going to skip this example, which is I knew I probably wouldn't have time for anyway, so I'm pretty close. So basically the summary is optimization over convex sets provides a framework that brings potentially difficult problems into reach. There are other optimization frameworks existing today, such as CVX and Yalmbet, but I think the Wolfram language, because we can do these transformations so nicely with our symbolic stuff, we've got a huge potential to put together something very nice and very automatic. And here are some new functions. I'll just let you look at that. That'll be coming down the pike sometime, and some changes to existing functions. So given that, we have a couple of seconds for questions. Okay, good enough.